Hi everyone, my name is Bir Bikram De. Today I'll be presenting design and construction of the Dragon Ball. In recent years, we are seeing more and more application of robots in hazardous environments. Example of such situation would be the deployment of Moni robots in Fukushima disaster, or how the SnakeBot was used for rescue operation in Mexico earthquake. More than 20,000 PackBot has been used to detect mines worldwide. While various other platform of robots have been tested, one platform that has not been tested is the spherical robot design. Spherical robots offers various advantages and disadvantages. Some of the advantages would be how easy it is to clean the robot, giving us a closed system where nothing comes in or nothing goes out. Maneuvering in complex environment is much easier for spherical robot. Also, the robot cannot be overturned. There are some challenges to this design as well, such as developing a control system, designing a robust system, and how to place the sensor in the robot. My contribution to this project is to come up with a systematic design process, design and manufacture a sealed robot, design a robust control system, and an intuitive visual teleoperation system. Now, let us look at previous works. All spherical robots can be divided into active and passive designs. A good example of passive design would be the Tumbleweed robot designed by NASA for planetary exploration. The active design can be further divided into rigid shell and deformable shells. Cohara robot is an example of deformable shell, where the shell of the robot can be deformed by the user's command. Now, rigid shells can be further divided by their internal drive or IDU. There are various design types and systems of IDUs. Analyzing such systems can tell us further about their advantages and disadvantages. A quick example of such system analysis can be done using the single wheel robot and the hamster wheel robot. Both of them are variation of direct drives. Advantages are that they can be manufactured easily. Disadvantages would be slippage. Now, it was important for me to come up with a systematic way to evaluate all the designs for our need. A popular systematic approach to evaluate various different designs is using house of quality, where a table is filled with requirements on the left side and the system design on the top. First, each requirements are ranked by their importance in our project. Then each system is evaluated against it, and finally the importance percentage was calculated. Notice this is an arbitrary evaluation and can be different from other projects. The highest ranking designs are gimbal mechanism and flywheel mechanism from this analysis. The main takeaway points are that we will be using the flywheel to turn and a gimbal drive to move forward. Now, let us look into designing and building the Dragon Ball. The overall idea was to design a robot where two domes are joined at the center with the essential electronics. Also, the dome should be made of carbon fiber to provide optimal strength and weight. Purchasing such dome would have costed us around like $10,000. So it was important for me to come up with a way to manufacture this in-house. I designed and developed a mold, cut pieces of carbon fiber cloth in the shape of a gore curve, stacked them in polar manner, and then epoxied them together to create the dome shape. The total cost was around $800 only. The internal layout of the Dragon Ball is shown in this diagram, where we can see how all the electronics is on the aluminum wheel and the dome cover it from both sides. Now let us look into how the robot is controlled. For spot turning, a bang controller is used to generate torque using the flywheel inside the robot. We can see the control system design from the image below. To move, different sets of turn can be generated using different sets of target torque values. Current possible sets of turn is shown in the picture on the screen. To move forward, Dragon Ball generates torque by moving the center of gravity forward, thus moving forward, essentially controlling the angle between the center of gravity and gravity vector to make the robot move forward or backward. Moving forward is achieved using a cascaded PID control as shown on the screen, where the inside loop controls the motor speed and the outside loop controls the IDU angle with respect to gravity. We can see how the cascaded PID control performs in comparison to a bang controller. The user input is shown in blue line. The IDU angle using the cascaded PID is shown in the gray line, and the IDU angle using a bang controller is shown using an orange line. Dragon Ball captures data from the cameras placed on the rolling axis on each side. Two 235-degree field of view cameras are placed on both sides to capture data. For visual teleoperation, the challenges were how to stabilize the images and how to modify them for the user to drive the robot. Dragon Ball uses data from the internal gyroscope to stabilize the incoming images. Dragon Ball uses a modified version of TiHo's work where the incoming images are dewarped using a lookup table. The lookup table contains a pixel location for each pixel where they should be, given it is an ideal spherical image. Then the image are stitched at the same after blending. Dragon Ball also offers a simulated pan-tilt system for the operator to monitor any region of interest. Now let us look at the image processing pipeline design for the Dragon Ball. From the user input, the zoom level is determined. Using that information, a lookup table is selected and cropped to the region of interest. Simultaneously, incoming images from the left camera and the right camera are stabilized. Then the lookup table are used to dewarp them. Both of the dewarped images are sliced at the center and then blended. All the images are then concatenated to form the final image. The GUI design offers user an easier way to operate the Dragon Ball. It also shows the current position of the robot using a real-time kinematic GPS system. Future work includes improving and implementing a CMG turn system and auto-generate turn set, also making the system fully autonomous. Thanks for listening. See you all in Romancy.